Welcome to my talk about ZFS Internal Structures. We will talk a little bit about bits, not about bits, but pointers and everything. I'm senior CE at Sun Microsystems, just recently finished my 17th year at Sun, and looking forward to the next opportunity at Sun, or Oracle or whatever. Okay, you all know this. ZFS is a file system of a new generation, has an integrated volume manager, has transactions for everything, for every change on the disk, checksums of every structure, self-healing, simplified administration, also accelerated administration, so inheritance. You can make changes online without recreating the ZFS, performance through control of the whole data path. And from time to time I get sentences from my customers that say, oh, ADVFS of digital had this, and we have checksums in our database for years and whatever, but everything in this combination, this is new. And this has also advantages, as we see now. Usually I then also come from the other side and tell the customers there is another explanation why we need ZFS. The current trends in the data centers are that we have larger file systems. Just recently I have seen an 800 terabyte file system. Data live longer on the disks now, much longer. Backup devices are sufficient for the daily changes, but usually it's very hard to buy enough tape drives to be able to restore in a disaster case everything in 1 or 2 hours. We just recently had a big bank asking us, we need 16 tape devices tomorrow for 2 weeks and want to pay them, but we need them for a restore because our database crashed. They had a burning disk array, and it was necessary to get everything back to disks, to new disks. By the way, the disks were also to be delivered tomorrow. So this causes problems. Even in the data, when we have the other things like larger file systems and everything, it's more difficult to be able to have a long-term storage very reliable. Even you have to take into account that copies on a disk are much more vulnerable as on a tape. On a tape, when a certain point is defective, only one file is affected. Perhaps you can get this file back from the other side, or can you cover it. But on a disk, you have essentially a tree structure. When one point is defective, in the upper part of the tree, lots of files can be harmed. And that's very much more vulnerable. Okay. ZFS and failures. ZFS can correct structural errors caused by bit errors or errors by mispositioning of the disk, and everybody says, this does not happen. This happens. If you look at documents of Seagate, for example, they tell it openly. And you look at the larger document, that is a 10-page document and a one-pager. The 10-page document is hard to find, but there it says that they have an error of an unrecoverable error by reading one sector by 10 to the power of 16 reads. 10 to the power of 16 reads of 512K are 5,000 terabytes. Okay, you never read 5,000 terabytes on one disk, but you think perhaps you have 1,000 disks in your data center, you have 2,000 disks, 10,000 disks in your data center, like the big banks have, and then it's 500 gigabytes to read, and that is read from a disk. Perhaps you have these errors every day. Errors are caused by mispositioning, and these numbers were on the older papers, but not on the new papers. You will not find the mispositioning errors on these disks. They never happen again. Okay, they happen, but they will not tell us. In the older papers, they tell that one mispositioning is happening every 10 to the power of 8 or 10 to the power of 9 positionings. I don't name this here because I want not to get sued. But This means on a normal disk, which I have today, which can perform 200 IOs per second, this happens every 2 weeks when it's in full use. So we have these errors. And usually we have the crashing system, or the system is not bootable anymore. And we all experienced, after reinstalling the system, miraculously it works. Why? Okay, DMA parity errors, bugs in software and firmware never happen, but ZFS can also check this through the checksums. And administration errors, somebody uses a disk for something other, and then ZFS behaves very much different than other file systems. So if you write to mirror, ZFS survives. If you write to mirror with any other file system, including UFS, X2, X3, whatever, it breaks the systems immediately. So how is this self-healing introduced into ZFS? It's an integrated volume manager, so that you know where the disks are, ZFS knows where the mirror is, where the RAID-Z configuration is, and you have large checksums inside of the block pointer instead of the small checksums on the disks. And how does it work? You read a block, which is determined by a block pointer, will be defined later. You create a checksum of the just read block and compares with the checksum which is in the block pointer. And after that, you can decide this block seems to be the block which is pointed to, or this block is wrong. This can be caused by error on the disk surface. This can be caused by mispositioning during this read. This can be caused by mispositioning during the time this block was read or was written. Yeah? But you can decide this block is wrong or this block is the right one. And because you have the integrated volume manager, you can use the other block if you have a mirror, or compute what this block should look alike when you have a RAID-Z configuration. I call this most of the time structural integrity. You know, in Star Trek spaceships, you have a force field which holds the whole spaceship into its form and hinders the gas to go out of the spaceship. We have this here also. Self-healing. And because I had a quote yesterday from another guy, it's different from other file systems. It's a quality not available from any other file system today. It's only possible when combining the integrated volume manager with a redundant setup and large checksums. And it's not available on Riser, X, Waffle, XFS, UFS, whatever. It's not available on these file systems. It will be available on PTRFS, which is a little bit designed after the features of ZFS when it's finished. But it's not finished today. And okay, I explained enough. I think I have to explain it. When I get the wrong block, I can detect this and can read the correct block and correct the wrong block and use only the correct blocks in the file system. So, what is this ZFS structure all about? Now we go into the deep structure. It consists of an uberblock. The uberblock points to the root of a tree. This is a tree. Computer scientists call this structure. And the tree has only data in the leaves of the tree. And these are the inner nodes of the tree. The inner nodes are also called metadata in ZFS speak. So this is the essential ZFS structure. Now we are finished, but I have some slides left. I will explain it in more detail. So you have the total guess how it's looking. And now we are starting with the structure, what is on a disk. A Z pool or a ZFS pool is built from whole disks or disk partitions or files. So for tests I can create a very small Z pool residing on files. Or for intermediate copying of data I can use a file consisting of parts which I have left on other disks, so I can copy around with this feature. And it's very nice to be able to do that. We prevented engineering from removing that feature, so be happy to have it today. Such an element, even if it is a file, we call it vdev, or physical vdev, because it's a physical virtual device. Okay. We have also other virtual devices. So the configuration of which we have in the ZFS can be a single device. So a part of the C pool consists only of a single device and is not in a redundant configuration. We have a mirrored device that we have for every place in the ZFS at least 2 devices. This is then a logical virtual device. And you can also use RAID 5 or RAID 6 methods with RAID C and RAID C2. And recently we introduced RAID C3 into OpenSolaris. You can get it from the dev repository, but it will be in the next OpenSolaris release also. And with these, you don't have a directly copy, you have a structure which consists of multiple disks which are put into a RAID. But we see it later, not each time you write something, the whole RAID width is used. It's sometimes a smaller RAID width is used. So that is one of the features of RAID C. And we also have the engineer who introduced RAID C3 thought about using RAID CN in the future so that we can have any number of disks failing. What is now the difference of a mirror of 4 disks to 4 disks and a RAID C4? Yeah, in the mirror, 4 disks can fail, but only 4 disks which do not match. In RAID C4, each combination of 4 disks can fail. So essentially, this is superior to mirror compared to availability. So what is the technical layout of a vdev? A physical vdev is laid out in this way. We have 4 vdev labels, which contains the information how the C pool is constructed. We look at the information of that in more detail now. And the next label, and the next slides. We have 2 labels at the beginning and 2 labels at the end. The idea is to use these 2 labels at the beginning and in the end, so that when you have an administration error and you have a 1 terabyte file, 1 terabyte disk, and you make an accident and write something into that, then these labels are destroyed, but the labels at the end are still living. So you have a chance to recover the C pool even if you have destroyed the first half of this physical vdev. Then we have a whole of 3.5 megabytes. This was intentionally thought of that you can put in some boot code there, but this is not used today. Even on the machines which have Z pool as root, they don't use this slot, but it can be used in the future. So the slot is always there. And then the rest is used as space for the C pool. And this is divided in 128 kilobyte blocks, and these blocks can be subdivided into smaller blocks, up to low to 512 bytes, and can be combined back up, what we will see later. Okay, everything clear. So we have this layout on every disk. This layout is on every disk. And now we have to describe what is some of these labels and then how the data blocks are used. So the vdev label contains 3 parts. First we have gap. So they will not use the first 2 8 kilobyte blocks because on these blocks we will have perhaps a disk label or boot code on x86. So these first 2 blocks are not used. There is nothing defined there. So we can put ZFS on a Sun labeled disk, for example, which needs the first 8 kilobyte block for its own label. And then, after that, we have the NV list. NV list is a structure which is defined in Solaris. You can find the definition inside of user include whatever, and that is all the main pages for that. NV list is a name and value pair list. This list contains the informations which make this pool up. One half is the attributes of the Z pool. For example, its name, its number, and whatever. We will see it in more detail. And then the second part is the whole configuration of the Z pool stored in this position. And then we have an uberblock array with 128 entries. Each is 1 kilobyte in size. And these uberblocks are the uberblocks which are used in round-robin fashion to store the latest number, so the latest pointer into the Z pool. And the uberblock array in each device, which is in 4 times there in each label, points to the root of the Z pool tree. This means that at each transaction we have 4 writes on each device. That's the way it's done. So because we have 4 writes on each device, it's done only every 5 seconds, which means less than one write per second. So it's essentially nothing. You cannot see it with IO stop because it's less than 1 write. So the configuration also defines logical vdevs. So if you do mirroring or READZILLA or a log device or a cache device, this configuration is going into this configuration storage. So how the Z pool behaves according to mirroring is essentially defined through this configuration, and the rest of the Z pool does not know about this. This is done on this level. So what's in this data? So we have this miraculous tool called ZDB. Did anybody use this up to now? ZDB, yeah. So ZDB has verbose feature. It's a -v, and that is a secret. You can use more than one -v. If you use more than one -v, it gets more verbose. If you need really everything, put in 8 -vs, and even a small Z pool is not. The output of even a small Z pool is not storable on this. It's very, very large. You get every detail. But with 2 -vs, you get this information. This is essentially the data Z pool on my laptop, and it's version 4. It's not the latest one, okay, and the name is data. The state is 0. So the state explains whether it is imported, which has the name 0, exported, which is 1, or destroyed, which is the value 2. Other values can be defined in the future. So there are other possibilities like shared Z pool or whatever. It's possible, but we don't think about shared Z pools today. Then we have a version number. So ZFS is working with transactions. So if you change a file, you are creating a transaction, and transactions are then grouped to transaction groups. And the largest transaction number which forms this transaction group is the transaction group number. So it's essentially a unique number in the system, and it's continuously growing. So you can compute it if you do a transaction every nanoseconds. The 64-bit transaction numbers will last beyond our lives, I think beyond the year 10,000, so it's enough. I think perhaps the year before the year 10,000, they changed to another file system. But perhaps sometimes earlier. So the pool has a global unique ID, which is made up from a checksum everywhere, but it's an ID of this pool when you create the pool. So each pool is identified by name and by the number. When you import a pool and you have 2 pools with the same name, you can distinguish between them by the different pool global unique ID. Contrary, that is a problem if you have 2 pools with the same pool GUID, then it's not possible to distinguish between them. The host ID is stored here. Which host is holding this pool today? the name of the host. My machine has a name Nuncio. My machines all have the names of characters of Robert Asprin. Who knows Robert Asprin? Nobody? Oh yeah. vdev tree. The vdev tree is so complicated because it's a configuration of the C pool. Next page. I had to use a smaller font. I have only one disk and it's this large. What is this vdev tree? So we have, this is essentially a structure. So it can have nested entries. I have only one disk inside of that, so I have the one slice used in that here. But you can also have mirrors, and the children are more distinguished. But some things are important. So this vdev logical number has ID 0. Then again, a unique ID. This is the same as here for 1. Yes, it's the same as here. So you have the connection to this pool. And here we have a disk. It can be also a file. It can be a partition. This will be indicated here. And then the real path where to find this device. After that, we have the device ID. Solaris uses, since Solaris 9, device IDs to be able to find this device even if it had a different number. So unfortunately, this device ID was so long that you cannot see the essential part. The essential part was outside of the screen, which contains the serial number of the disk. So with the serial number of the disk, it can distinguish between different disks. And a physical path. This is a physical path, which is essentially the link where this points to. So the ZFS import is able to import a pool even if the disk has changed the position, because it has a device ID, it has also the position where this disk is there, and it's able to find this. So this is the whole disk, so it can be indicated here. It's a partition in my case. Metaslab array, metaslab shift. This is a storage where the disk's free space is organized, and each disk has a number of blocks, and the number of blocks is limited on this disk. So you know what is the size of the disk, and you have an object or a list of stuff which hangs behind that, and they are using this lab allocator. Jeff Bonwick did the main memory allocation algorithm for Solaris before he did the ZFS, and the main memory algorithm is using an algorithm which is called slab allocator, and now we are using the same algorithm on the disk. It's designed with that one, and the A size is the real size of the disk, the allocated size, the A size. Okay. Remember, here is the ID 0. The ID 0 designates which disk is used, the vdev. We need this later. So, we now know what is on the label. And the uberblocks are simply blocks which contain a magic number, a version, a transaction group number, a timestamp, and a checksum. So the uberblock is checksummed in itself. With that, I can detect which is the uberblock with the largest transaction group number, and I can check the timestamp also with that, so that I can get the most recent uberblock and check whether it is in the consistent inside of itself. And with that, I have verified this is the newest uberblock, and it has only one content, the pointer to the root of the C pool tree. This, the latest uberblock, contains a pointer, and this can be on any of these disks in the C pool, and this gives me the information about the contents of the stuff. Perhaps you should look at the magic number. It's 0x00BAB10C. 0C, okay, 0C. So, speak it. Uberblock. They're making jokes also in engineering. And this number is, the sequence is important because ZFS is a file system which can exist on x86 and on Spark. Spark is big endian, x86 is little endian, and the sequence is different, and you know on which endianness this block is written. Because you look how the uberblock is written there. So the uberblock is written as a number, so the sequence is inside of this number visible. So we have to look at the uberblock. What's that? Again, my dear disk here has a magic number, and you see it's on the same machine written as the uberblock is now read. Version 4, transaction group number, the ID and the timestamp when it's written, and now the root boot pointer. So the root boot pointer will be explained now, and therefore I have no details here on this page. So the block pointer, and then not a boot pointer, block pointer. The block pointer contains so-called data virtual addresses. So a data virtual address points to another block. This is essentially the basic thing which points to a block. And to find the other block which can reside on another vdev, we have a vdev number inside of this. So this is the ID I showed you before in the vdev designation. So here is simply a number. And when you go to this vdev, then you find this block. The number of block in the vdev, okay, this is the offset or number of block where you can find this block. And a grid information, this is necessary when you are using RAID-Z to know which width this block is now written, because you can write in smaller widths. And the grid information says which of the RAID-Z blocks are used for this block. And a gang width. Gang. What is a gang? A chain gang is used in the United States when they used was heißt strafgefangen? Convicted fellows from the prison, and they have to clean the streets, have to build houses, have to build government buildings and whatever. They're chained with their knee angles together, so 6 or 10 together, and they clean the street in a row. And this gang bit says, if I switch on the gang bit here, then I don't have these large blockers from 128K in my system. I have too much fragmentation. But I can collect a number of these blocks together to build a 128K block again. And this is indicated by a gang bit. Then this pointer is not to a real block. Then this pointer goes to a gang block, which is 512 byte, which is the smallest size, so I have it all the time. And the smallest size collects other blocks together to a 128K block. This is done as a gang bit. Type and size of a block. So what is this block? So this block can have different types. It can be a directory, it can be data, it can be metadata, whatever. I will not go into detail because there are around 50 types of blocks there. So when you want to know something about that, look at the paper, and there is a reference to the on-disk format, and they explain all the types of blocks there. And you have an allocated size. How large is this block allocated? So it can be in different data virtual addresses in different size. Compression information, is this block compressed, and with which algorithm is it compressed, and what is the size of the compression? So if you have a compression, it's usually smaller, and if you have a block which is around 32K, then after the compression it can be 16K or can be 8K, and it's stored what is the original size and what is the compressed size, and only the compressed size needs to be allocated. But the allocated size can be larger than the compressed size, for example, if you want to trade speed for time. size for speed, yes. Okay, a transaction group number as again, and a checksum of the whole block where these pointers are pointing to. And these data virtual addresses point to essentially the same block. Some blocks in the system are stored more than once. And one point where you see this, since some updates in Solaris, you can use the attribute copies for your data. And if you set copies to 2, then each pointer here to data is using 2 data virtual addresses and stores blocks 2 times of the same on the devices. And it tries to use different devices if you have more than one device. You can also set copies to 3 and not more than 3 because you have the limit of 3 data virtual addresses inside of a block pointer. That's the reason, because we have a limit on copies. Okay, what's this all about? This block is 400 logical size and 200 physical size. This means it's a 4-bit, 8-bit, and 2-bit from the 4, the 10-bit. So these are this block has a size of 1024 bytes. 10 minutes. Oh, cool. And it is compressed, so I need only 512 bytes. I have 3 data virtual addresses, all on the same device, 000. These are the positions, and these are the compressed sizes, as you see above. The block is checksummed with Fletcher Force checksum and compressed with LZJB, the first compression algorithm which is there. And it's contiguous, it's not game chained. The birth was at this time, as this transaction group number. And this is the rest which is filled with stuff because the 512K are not filled. And this is a checksum of the block where this pointer points to. This is the structure of a block pointer. 10 minutes. Oh. So essentially, a ZFS looks like that. So I painted some pointers here. There are much more pointers. Much more. And each of these labels has this root pointer, which I only indicated once. So, transactions, we had this before. You can imagine, everybody of you had seen this in my presentation, so I skip it because of a lack of time. DMU objects. An object is defined by a so-called dnode. It's an object. DMU means data management unit. And this is essentially type and size. What is this for an object? Is this a directory? Is this data? Is this object list? Is whatever? What is this? Indirection depth. A list of block pointers. The list is limited. So in this structure, there we have only space for 3 block pointers at most. And then a bonus buffer. Bonus buffer, remember that? I'll tell it now because I don't know whether I have 10 later. The bonus buffer contains, when this object is a file, it contains the file attributes of the Unix file. And the bonus buffer is used on different types of objects in a different way. So sometimes you find some other pointers inside of that. For example, in an object set, you find the pointer to the ZIL inside of that, and so on. The DMU object set, which is essentially an object, which is an array containing only dnodes. Such a dnode has a fixed size of 512K, so you can simply address an object set. This is one data object containing 512 byte. I said K, it's only 512 byte size objects, and each one can be addressed by an index. That's the way it is. So, the structure is this way. So, you have a dnode object, which has 3 block pointers here. And these 3 block pointers, this is an excerpt from this structure here, and they have data virtual addresses which point to copies of pointers, and they go down, as I explained on the initial slide where I showed the tree structure, but only we have a multiple copies of these pointers every time. So why multiple? Why these pointers are very important. So it's very important to have them in a multiple way. Pointers which contain metadata which are essential for the Z pool are all the time stored in 3 copies, and pointers which are essential for a ZFS file system are all the time stored in 2 copies. And the default for data is 1 copy, because you have this mirror stuff. But you can also increase the number of copies here by the attribute copies of the ZFS file system. So this is an object. So object is a squared case. 5 minutes ago. Okay. Intent log, I already explained. The dataset and snapshot layer uses now these objects and object sets. Object is a single pointer, object set is an object containing an array, and build these things, a file system, a snapshot, clones, ZFS volumes. So, and the least recent uberblock pointer points to a so-called meta object set. It has 1 or 2 more fields inside of this. And this meta object set, I think I use the structure here, has everything inside of that. Okay, I use this thing. So I have the uberblock pointer. This points to this DSL directory. The DSL directory is an object. And then this DSL directory essentially has 3 entries. One entry is for the properties of this ZFS object. Then another object which is the DSL dataset. This is only 1 entry, and this points to an object set. Remember, the object which contains object pointers. And these are the files and directories of the ZFS file system. If you have snapshots, they are linked here from this DSL dataset via a linked list. And all the magic of freeing up the data is controlled by the ZFS code. So the structure does not know about this. It's only stored in this slab stuff, which I explained before. And ZFS has hierarchical names. This is done by another object here in this DSL directory. It's called the DSL child dataset. And this is also a ZAP object. This is like a directory. I explained it immediately. This is the last thing I can explain. And this contains then the subdirectory. So here I have, when I have a pool tank, I have home and home1. These are 2 entries in this directory, and behind each of these pointers we have here the DSL directory of the sub file system. So they are linked in this way. So now I have to explain how these attributes are stored. The attributes are stored with the ZFS Attribute Processor. The ZFS Attribute Processor essentially holds name-value pairs. This is a hash table with overflow lists, and it's used for directories, ZFS hierarchical names, and ZFS attributes. Even when you have user attributes, these are stored in this ZAP processor. Okay, and when you have a point where you have a ZAP, it can be a micro-ZAP or a fat-ZAP. These are essentially the same thing, but a micro-ZAP is 128K, it's only 1 block, and everything is done in this block. Usually you read this block at once, and you can process all the attributes inside of this. The attributes of a ZFS file system and the attributes of a file all fit into this 1 block, so usually you need not more than 1 block. And the fat ZAP is used if you have a large number of attributes. If you need more attributes than this, for example, for the large directories inside of a ZFS file system, then you need a fat ZAP. A fat ZAP is an object with arbitrary size. It has an own binary structure inside of that. And the first part is a pointer table, which can be adjusted in size. And this pointer table is hashed, and the pointers go to the storage where the name value pairs are stored. And the difference is I can only have simple attributes here, only a 64-bit number, up to a 64-bit number, and here I can have arbitrary attributes.